A rare visitor from deep space is flying through our solar system, and this one is, honestly, mind-blowingly mysterious. 3I Atlas came from beyond our solar system, making it only the third confirmed interstellar object ever discovered. But, new data from NASA and international observatories suggests this ancient traveler might be something far more extraordinary than just another comet racing past the sun. The breaking discovery. On July 1, 2025, astronomers using the NASA-funded Asteroid Terrestrial Impact Last Alert System telescope at Rio Hurtado, Chile, made a breakthrough discovery that would, captivate the global scientific community. They detected a moving object initially designated as A11PL3Z, later confirmed as 3I Atlas, representing the third known visitor from beyond our solar system. This rapid confirmation was achieved through combined efforts of international observers, including the Minor Planet Center and researchers at NASA's Jet Propulsion Laboratory. The object's initial detection proved challenging due to its faintness and location near dense star fields close to the galactic center in the constellation Sagittarius. High-precision astrometric measurements soon revealed its distinctive hyperbolic trajectory and extreme velocity, definitively eliminating the possibility it belonged to our solar system. 3I Atlas's discovery immediately energized astronomers worldwide, sparking an unprecedented campaign of rapid, coordinated observations designed to track this rare interstellar visitor, while maximizing data collection before it became too dim to observe effectively. This extraordinary find underscores the remarkable capabilities of modern telescopic survey systems in uncovering objects once believed completely undetectable, opening new scientific horizons for comprehensive interstellar object research. The discovery story. Between June 25 and 29, 2025, the Atlas survey system, composed of 4 powerful telescopes strategically located in Hawaii, Chile, and South Africa, captured multiple critical detections of the newly discovered object, now officially known as 3I Atlas. The initial observational data appeared as extremely faint streaks against the dense starry backdrop, but gained tremendous scientific significance as coordinated follow-up observations quickly pinpointed its precise celestial path. Simultaneous observations from the Zwicky Transient Facility at Palomar Observatory in California, strongly supported by dedicated researchers like Marco Micheli from the European Space Agency and Daryl Seligman from Michigan State University, helped definitively confirm the object's unbound hyperbolic trajectory, providing compelling evidence supporting its confirmed extrasolar origin. The survey system's remarkable ability to rapidly scan vast areas of sky using advanced wide-field imaging technology proved absolutely critical in detecting this extraordinarily rare interstellar visitor amidst the incredibly dense stellar population near the galactic center, where precise object identification remains notoriously challenging. Extensive archival searches later uncovered valuable pre-discovery observational data dating back to June 14, definitively revealing that this ancient comet had been silently traversing our solar neighborhood for several weeks before achieving formal astronomical recognition and official designation. A stranger in our midst. What makes 3I Atlas truly extraordinary are its unprecedented physical characteristics that, honestly, challenge conventional understanding of interstellar objects. Moving at an absolutely mind-boggling speed of approximately 58 kilometers per second relative to the Sun, this cosmic visitor dramatically outpaces both previous interstellar visitors, Oumuamua and 2I Borisov. Its extreme orbital eccentricity of 6.14 represents the highest value ever recorded for any known celestial object, creating an almost perfectly straight trajectory through our solar system. Initial size estimates suggested the object could measure up to 20 kilometers in diameter, making it potentially the largest interstellar visitor ever observed, though recent Hubble Space Telescope observations indicate a more modest size between 0.32 and 5.6 kilometers. The comet's unusual brightness patterns and early activation, while still 4.5 astronomical units from the Sun, have puzzled researchers worldwide. Unlike typical comets that remain dormant at such distances, 3I Atlas began displaying cometary activity far earlier than theoretical models predict, suggesting either unique composition or potentially artificial characteristics. Its trajectory alignment with the ecliptic plane occurs with only a 0.2% probability by random chance, raising questions about whether this positioning might be deliberate rather than coincidental, adding another layer of mystery to an already enigmatic cosmic visitor. The predecessors. The discovery of 3I Atlas follows two other remarkable interstellar visitors that, really revolutionized our understanding of cosmic wanderers. Oumuamua, discovered in October 2017 by astronomer Robert Warwick at the University of Hawaii, became the first confirmed interstellar object. It measured roughly 400 meters long and had this unusual elongated shape. Its mysterious acceleration patterns sparked intense scientific debate, with some researchers even proposing exotic explanations including possible artificial origins. 2 years later, amateur astronomer Gennady Borisov discovered 2I Borisov in August 2019, which turned out to be a more conventional interstellar comet with typical outgassing behavior and composition. These three visitors demonstrate that interstellar objects may actually be far more common than we previously believed, with improved detection capabilities now revealing a steady stream of cosmic travelers passing through our solar system. The objects display varying characteristics. Oumuamua appeared asteroid-like with no visible coma. Borisov behaved like a typical comet, while 3I Atlas exhibits these hybrid features that just don't fit established categories perfectly. This progression suggests our solar system regularly encounters material ejected from other stellar systems throughout the galaxy, providing, honestly, unprecedented opportunities to study the composition and formation processes of distant planetary systems, without needing to mount expensive interstellar missions to reach them. The cosmic journey. 3I Atlas follows a precisely calculated path through our solar system that brings it tantalizingly close to multiple planets during its brief visit. The comet will reach perihelion on October 30, 2025, approaching within 1.36 astronomical units of the Sun, positioning it between Earth and Mars at its closest solar approach. During its journey, the object will pass remarkably close to several planets: 0.19 AU from Mars on October 3, 0.65 AU from Venus on November 3, and 1.8 AU from Earth on December 19, 2025. These planetary encounters offer honestly unprecedented scientific opportunities to study an interstellar visitor using various spacecraft instruments and ground-based observatories positioned throughout the solar system. The comet's retrograde orbit, inclined 175 degrees relative to the ecliptic plane, means it travels opposite to the planet's orbital motion, adding to its mysterious nature. Computer models tracking its future trajectory indicate 3I Atlas will eventually pass 0.36 AU from Jupiter on March 16, 2026, before departing our solar system forever. This cosmic journey provides a once-in-a-lifetime opportunity for comprehensive multi-wavelength observations, gravitational studies, and potential spacecraft encounters that could, really unlock secrets about the formation and evolution of planetary systems beyond our own solar neighborhood. A scientific goldmine. The arrival of 3I Atlas presents astronomers with an unprecedented scientific opportunity to study pristine interstellar material using cutting-edge technology that just wasn't available during previous visits. NASA's Hubble Space Telescope captured detailed images in July 2025, revealing the comet's coma structure and dust distribution patterns. The James Webb Space Telescope is conducting comprehensive spectroscopic analysis to determine the object's chemical composition, searching for exotic materials or isotopic ratios that differ from solar system objects. Ground-based observatories worldwide, including the Gemini Observatory and Keck Observatory, are monitoring brightness variations and rotational periods that provide insights into the comet's internal structure and density. Advanced computer modeling allows researchers to simulate the comet's behavior under various theoretical scenarios, testing whether observed characteristics match predictions for natural formation versus artificial construction. International collaboration through organizations like the European Southern Observatory ensures continuous monitoring across multiple wavelengths and time zones. The wealth of data being collected right now far exceeds anything obtained from Oumuamua or Borisov, potentially revolutionizing our understanding of interstellar objects, planetary formation processes, and the dynamic environment between stellar systems. This comprehensive scientific investigation may, hopefully, provide definitive answers about 3I Atlas's true nature and origin before it disappears into interstellar space forever. Unanswered questions. Despite intensive international observation campaigns, 3I Atlas continues to pose fundamental questions that challenge our understanding of interstellar objects and their origins. The comet's exact size remains uncertain due to its surrounding coma of reflective dust, which obscures the nucleus and complicates accurate diameter measurements. Early estimates range from 1 to 2 kilometers to potentially 20 kilometers across, representing enormous uncertainty that affects calculations of mass, composition, and internal structure. Dr. John Noonan at Auburn University suggests the nucleus is likely on the smaller end of this range, comparable to 2I Borisov, but definitive measurements await future observations. The object's unusual chemical composition, revealed through spectroscopic analysis, contains isotopic ratios that don't match typical solar system materials, raising questions about the stellar environment where it formed billions of years ago. Its remarkably preserved surface state, despite potentially eons of cosmic ray exposure, challenges models of interstellar weathering and erosion processes. The comet's early activation and controlled outgassing patterns differ significantly from known cometary behavior, suggesting either exotic ice compositions or, possibly, artificial regulation mechanisms. Most puzzling is the statistical improbability of its trajectory alignment and planetary encounter sequence, which some researchers argue exceeds reasonable expectations for random cosmic debris, opening discussions about whether 3I Atlas might represent something more deliberate than natural space debris. The alien question. The possibility that 3I Atlas represents artificial technology rather than natural cosmic debris has sparked intense scientific debate, led prominently by Professor Avi Loeb from Harvard University. Loeb, co-founder of the Galileo project dedicated to searching for extraterrestrial technology, co-authored a controversial paper suggesting the object could potentially represent hostile alien technology based on its unusual trajectory and behavioral patterns. His analysis points to the object's statistically improbable path through our solar system, perfect timing for planetary encounters, and controlled thermal emissions as potential evidence of artificial origins rather than random cosmic wandering. However, the majority of mainstream astronomers strongly reject these claims as premature speculation lacking sufficient evidence, emphasizing that natural explanations remain more plausible for all observed characteristics. Critics argue that entertaining artificial hypotheses without definitive proof undermines scientific credibility and promotes unfounded conspiracy theories about extraterrestrial visitation. The debate highlights fundamental questions about scientific methodology when confronting potentially paradigm-shifting discoveries. Should researchers explore all possible explanations regardless of how extraordinary, or maintain conservative approaches that prioritize conventional interpretations? This controversy reflects broader tensions within the astronomical community about balancing open-minded inquiry with rigorous skepticism when studying objects that challenge established models of natural phenomena and cosmic evolution. Observing the visitor. Astronomers worldwide are employing every available technological resource to study 3I Atlas before it fades from observable range forever. NASA's Hubble Space Telescope continues capturing high-resolution images to monitor changes in the comet's coma and potential tail development as it approaches perihelion. The Swift Observatory is measuring water vapor emissions and ultraviolet signatures that provide insights into the comet's internal ice composition and sublimation processes. Ground-based facilities, including the Very Large Telescope in Chile and Mauna Kea observatories in Hawaii, are conducting continuous photometric monitoring to detect brightness variations, rotational periods, and potential outburst events. Radio telescopes, including the Green Bank Observatory, are searching for any electromagnetic emissions that might indicate artificial communication systems or technological signatures hidden within natural thermal radiation. Advanced spectroscopic instruments are analyzing the comet's chemical fingerprints across multiple wavelengths, comparing isotopic ratios and molecular compositions with known solar system materials and theoretical predictions for interstellar objects. Amateur astronomers using sophisticated backyard telescopes are contributing valuable time series observations that fill gaps between professional facility scheduling. This unprecedented global observational campaign represents the most comprehensive study ever conducted of an interstellar visitor, potentially providing definitive answers about 3I Atlas's true nature and implications for our understanding of cosmic intelligence and planetary system evolution. Dawn of a new era. The discovery of 3I Atlas marks the beginning of a revolutionary era in interstellar object detection and analysis, fundamentally transforming humanity's understanding of our cosmic environment. Dr. James Davenport emphasizes that upcoming facilities like the Vera Rubin Observatory are expected to revolutionize detection capabilities, with projections estimating dozens to hundreds of similar discoveries during its operational decade. This technological advancement will enable comprehensive statistical studies of interstellar object populations, their frequency, composition, and origins, providing unprecedented insights into galactic dynamics and planetary system evolution throughout the Milky Way. The European Space Agency's JWST Spectroscopy Division continues developing new analytical techniques specifically designed to distinguish between natural and artificial characteristics in future interstellar visitors, preparing for potential discoveries that might challenge fundamental assumptions about cosmic intelligence. Advanced computer modeling and machine learning algorithms are being developed to rapidly process vast amounts of observational data from multiple sources, identifying subtle patterns and anomalies that might escape human analysis. International cooperation frameworks established during the 3I Atlas investigation will serve as templates for coordinated responses to future discoveries, ensuring maximum scientific return from these rare cosmic opportunities. The broader implications extend beyond astronomy, potentially affecting planetary defense strategies, exobiology research, and humanity's philosophical understanding of our place in a universe that may be far more dynamic and populated than previously imagined. As 3I Atlas continues its journey past the Sun, it leaves behind more questions than answers about the true nature of interstellar visitors. Whether this ancient cosmic wanderer represents natural debris from a distant star system, or something far more extraordinary, its discovery has opened new frontiers in astronomical research. The truth about 3I Atlas may reshape our understanding of intelligence in the cosmos. Keep exploring with Simply Science. Like, share, and subscribe for more cosmic revelations.
A comet near the Sun just exploded in brightness, its tail now fanning wider than 5 full moons. Just days later, the Sun unleashed its most powerful flare in months, blasting a wave of plasma straight toward that same comet. Now, that comet, R2 Swan, is heading toward Earth, fast. In a few short weeks, it will make its closest pass just as an interstellar object aligns with it in the sky. What happens when a cosmic visitor meets solar fire? Let's explore this together.
First light. The outburst begins.
Comets are notoriously unpredictable, but what happened on September 26th caught everyone by surprise. Just 2 weeks after its closest pass to the Sun at a perihelion of 0.5 astronomical units, Comet Swan suddenly roared to life. Initially, it was a faint object, but amateur astronomers in Japan and Australia noticed a dramatic surge in brightness overnight. This wasn't a minor flicker. The comet's brightness leaped by a full magnitude, from 7.4 to a peak of 5.7, pushing it into naked-eye visibility under dark skies. What caused this? As the comet swung away from the Sun, intense solar heat penetrated its frozen nucleus. Pockets of sublimating cryovolatiles like frozen carbon monoxide and carbon dioxide buried for millennia reached their breaking point and exploded through the crust. This outburst ejected a massive cloud of gas and dust, dramatically expanding the comet's atmosphere, or coma, and feeding its enormous tail. According to cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory, such outbursts provide a rare glimpse into the primordial material from which our solar system was formed. This event signaled that Swan's inner engine was now exposed, making its next moves completely unpredictable and turning it into a prime target for skywatchers worldwide. The sudden release of energy was so significant it altered the comet's light curve, deviating sharply from all predictive models.
Anatomy of a tail.
What does it really mean for a comet's tail to be wider than 5 full moons? Let's put that into perspective. We're not talking about a small, fuzzy patch in the sky. This is a massive structure, stretching over 2.5 degrees, which translates to a physical length of millions of kilometers. For observers, even in suburban areas, this makes it a stunning sight in binoculars. A comet actually has 2 distinct tails. The first is the dust tail, made of heavier particles pushed back by the pressure of sunlight itself, giving it a yellowish-white glow. This tail curves gracefully as it follows the comet's orbital path. The second, and often more dramatic, is the ion tail. This is composed of gases that have been ionized by the sun's ultraviolet radiation, creating charged particles like carbon monoxide ions CO+ that glow with a distinct electric blue light. Because these particles are electrically charged, the ion tail is sculpted by the solar wind and its magnetic field, always pointing directly away from the sun. With Swan's tail being so expansive, even small telescopes can reveal incredible details. Knots of dust, shifting streamers, and sudden kinks. Amateur astronomers are already capturing these changes, creating time lapses that show the tail evolving hour by hour. This massive, unfurling tail isn't just for show. It's a giant, sensitive windsock in space, about to get hit by a solar storm.
The sun awakens.
Just as the comet was putting on its show, the sun, which had been quiet for weeks, decided to join the party with its most powerful eruption in months. On September 28th, at 0843 Universal Time, satellites from the GEOES network detected a massive spike in X-ray emissions, jumping from a background level of 10 to the -6 to 6.4 times 10 to the -5 watts per square meter. An M6.4 class solar flare had erupted from a magnetically complex sunspot group, designated Active Region 4232, then rotating into view on the sun's southeastern limb. M-class flares are the second strongest category, and a 6.4 is a significant event, powerful enough to cause radio blackouts on the sunlit side of Earth. Scientists at NOAA's Space Weather Prediction Center, like lead forecaster Dr. Alexei Pevtsov, immediately began analyzing data from the Solar Dynamics Observatory's AIA instrument at multiple wavelengths, including 131 angstroms, to assess the flare's power and, more importantly, what it threw into space. The energy release was equivalent to millions of hydrogen bombs detonating simultaneously. The timing was incredible. Just 2 days after the comet's own eruption, the sun had fired a warning shot into the exact same quadrant of space.
Plasma on the move.
So, what is a coronal mass ejection? It's a massive eruption of plasma and magnetic fields from the sun's outer atmosphere, the corona, releasing billions of tons of material into space. Think of it as a solar cannonball. This particular CME shot out from the sun at a speed estimated between 800 and 1,000 kilometers per second. Forecasters at the NOAA Space Weather Prediction Center quickly began running its trajectory through their WSA-NLEL model, a sophisticated computer simulation that predicts how solar disturbances travel through the solar system. Using data from coronagraphs on satellites like the Solar and Heliospheric Observatory SOHO, which create an artificial eclipse to see the sun's faint corona, they determined the CME was not aimed at Earth. Instead, the model showed its path would sweep directly through the sector of space occupied by Comet Swan. The timing was remarkable, just 2 days after the comet's major outburst. This set up a rare opportunity for scientists to watch what happens when a powerful solar storm collides with a comet. The plasma density in the CME, while incredibly thin by earthly standards, is more than enough to overwhelm the comet's own magnetic field. The question for forecasters was no longer if the CME would hit, but when, and how dramatically it would affect the comet's enormous, newly expanded tail.
Magnetic scissors.
So, what happens when a comet's tail, which is a magnetic structure, meets a massive magnetic cloud from the sun? Sometimes things just snap. This phenomenon is called magnetic reconnection, and it's one of the most explosive processes in the solar system. A comet's ion tail is made of plasma, held together by magnetic field lines streaming away from the sun. A CME, however, is a tangled web of powerful magnetic fields, often containing a strong southward-pointing component, known as the Bez field. If this southward Bez field, with a strength potentially exceeding 20 nanoteslas, slams into the comet's oppositely directed magnetic field, they can't merge. Instead, they collide, break apart, and explosively reconnect into a new shape. As space plasma physicist Dr. James Drake has explained, This process converts magnetic energy into kinetic energy with incredible efficiency. When this happens, the energy release can be immense, acting like a pair of magnetic scissors that cleanly severs the entire ion tail from the comet's head. This is called a disconnection event, and it can happen in a matter of minutes, leaving the old tail to drift away as a new one begins to form.
The forecasters puzzled.
Predicting the outcome of this cosmic collision is a huge challenge. While models showed the CME heading toward Comet Swan, solar ejections don't travel in perfect straight lines. They expand and can be twisted by the ever-present solar wind. The best estimates from the SWPC place the CME's arrival at the comet between 48 and 72 hours after it left the Sun. The key uncertainty was whether the most intense part of the CME with a strong southward BZ component would score a direct hit on the ion tail. Without a direct impact on Earth, scientists have limited in situ data. However, data from spacecraft like NASA's Stereo-A, which observes the Sun from a different vantage point, helps create a three-dimensional picture of the CME, improving the forecast. Dr. Carl Battams, of the U.S. Naval Research Laboratory, a leading expert on comets observed by SOHO, noted that these events are nowcast situations, where data is analyzed as it arrives with little room for error. Every major forecast center flagged the event for comet researchers worldwide. For Earth, the risk was zero. For Comet Swan, however, the incoming plasma was a loaded gun. The world's astronomers were now watching, waiting to see if the tail would simply ripple or completely break apart.
Citizen science mobilizes.
When a cosmic event like this unfolds, the big observatories aren't the only ones watching. A global network of backyard astronomers becomes the front line. Professional telescopes have schedules booked months in advance, so they can't always drop everything to watch a single event. Citizen scientists, however, can provide continuous, round-the-clock coverage. This is crucial, because a tail disconnection event can be incredibly fast, unfolding in less than 2 hours. An amateur astronomer with a modest setup, like a 10-inch reflector and a modern CCD camera, could be the first person to capture the collision. Organizations like the Association of Lunar and Planetary Observers, or ALPO, have entire sections dedicated to coordinating comet observations. Renowned astrophotographer Damian Peach has shown how high-resolution amateur images can rival those from professional instruments. These observers are not just taking pretty pictures. They are collecting valuable scientific data, or photometry, that can be used to measure brightness changes and map the tail's structure with incredible detail, helping to build a global record of this rare encounter.
The perfect alignment.
As if a dramatic outburst and a solar storm weren't enough, the cosmos has thrown in another twist. On October 21, 2025, Comet Swan will make its closest approach to Earth, passing just 0.26 astronomical units, or about 39 million kilometers away. This close pass is remarkable for another reason: the timing. It occurs during a new moon, meaning the sky will be at its darkest, providing perfect viewing conditions. And there's more. On the very same day, an interstellar visitor designated 3I Atlas will be in the same general region of the sky from our perspective. While separated by millions of kilometers, this alignment offers a rare chance to compare a comet from our own solar system with an object like 2I Borisov, which had a distinctly different chemical composition. Such alignments are invaluable for testing our models of solar system formation and planetary science. The geometry of Swan's close approach also enables a cool trick for amateur astronomers: the parallax effect. Because the comet is relatively close, its apparent position against the background stars will shift measurably when viewed simultaneously from different locations on Earth, allowing backyard observers to triangulate its precise distance.
Southern skies spotlight.
For these crucial weeks, the best seats for this cosmic show are in the Southern Hemisphere. From major observatories like the Siding Spring Observatory in Australia to backyard setups in South Africa and South America, Comet Swan will be high in the sky after sunset. Its path takes it through the southern constellations of Grus and Piscis Austrinus, passing near the bright guide star Fomalhaut. Viewers can use this star as a guidepost to locate the comet, which will appear as a fuzzy star with a long, faint streak extending from it. Even a standard pair of 7x50 binoculars will be enough to reveal the tail, stretching over 2.5 degrees, the width of 5 full moons. For those in the northern hemisphere, the view will improve throughout October as the comet climbs higher in the western sky after midnight. The checklist for observers is simple. Find a dark sky, use a star chart to locate the comet, and watch for any changes. By taking images every few minutes, observers can create time lapses that will reveal the tail's motion and any sudden disruptions caused by the solar wind in stunning detail.
Cosmic forces collide.
Let's bottom line this. We have a documented encounter between a powerful solar storm and a comet that has recently undergone a massive outburst. Scientists are eagerly waiting to see the effects of the CME, reminiscent of the 2007 event, when NASA's Stereo spacecraft watched a CME completely rip the tail from Comet Encke. Dr. Geraint Jones of University College London, who studied that event, emphasizes that these collisions allow us to probe the comet's invisible magnetic environment. However, it's crucial to note that the exact outcome for SWAN remains to be seen, and no direct link has been scientifically established between the M6.4 solar flare and SWAN's earlier outburst. The timing is likely a spectacular cosmic coincidence. What is certain is that this October provides an unprecedented window for both professional and amateur observers to witness the dynamic interplay of cosmic forces in real time. Key questions remain. How much material will be stripped from the tail, and what can that tell us about the comet's composition and the sun's power? The journey of Comet R2 SWAN is a rare and unfolding story, a live experiment in solar system physics happening right before our eyes. We are witnessing a truly unique cosmic alignment, a volatile comet, a powerful solar storm, and a front-row seat from Earth. What will happen when the CME slams into SWAN's tail is still unknown. Will it be a gentle ripple or a dramatic disconnection that severs the tail completely? The only way to find out is to look up. This is a rare opportunity for anyone with a pair of binoculars or a small telescope to contribute to a global science campaign. The universe is putting on a show, reminding us of the immense and unpredictable forces at play. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Simply Science.
What if the most important photograph in human history looked like a complete failure? We have the first clear images of 3I Atlas, the third interstellar object ever detected, and they show a blur, a smudge that refuses to focus. But hidden within that haze is a traveler older than Earth, an object moving at the very edge of physics. NASA doesn't want you to see how strange it is, but the truth is coming out. So, what secrets does this blur actually hold? Let's delve into it. Chasing motion. How do you photograph something that refuses to stay still? Capturing 3I Atlas wasn't like shooting an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects a few seconds of light, the object has already traveled thousands of kilometers, moving at a blistering speed of roughly 12 kilometers per second relative to the sun. A single frame would show nothing but a soft, meaningless streak. To overcome that, as orbital dynamics expert Davide Farnocchia can attest, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time to keep the magnitude 17 object perfectly centered on the sensor. For context, that is over 25,000 times fainter than the faintest star visible to the naked eye. As a result, the stars in the background blurred into trails, but 3I Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out. The challenge is immense. Even a tiny error in the predicted trajectory would smear the object into invisibility. This wasn't just a photo, it was time made visible, a precise balance between the comet's impossible speed and the telescope's relentless pursuit, a feat of engineering that astronomers at the Minor Planet Center work to perfect daily. Shape without surface. So what does this interstellar traveler actually look like? Here's where things get strange. In the image, 3I Atlas shows no surface. There is no crisp edge, no solid nucleus shining at its center. What we see instead is an outline that refuses to stay defined. a gray body that fades into itself. The elongation is unmistakable, it is not round, and it's not a random smear. It holds a deliberate structure, smooth at one end and uneven at the other. If this were a comet from our own solar system, we would expect a classic teardrop shape with a tail tapering behind it. But 3I Atlas shows a body that seems evenly stretched, almost like a cylinder with no clear tail direction. This has puzzled every scientist studying it. The shape seems to hint at a rapid rotation, blurring its features together the way a long shutter turns moving water into a flat, silky surface. The team, using methods similar to those pioneered by Karen Meach for Oumuamua, detected a faint brightness variation suggesting a length-to-width ratio of approximately 3:1. This is far less extreme than Oumuamua's 10:1 ratio, but it makes the object's lack of a coma even more baffling.
The absence of color.
What can a lack of color tell us about an object's past? When astronomers processed the raw images of 3I Atlas, they found something curious: no real color. Most comets show at least a hint of tone, like a greenish halo from cyanogen gas. But this object gives almost nothing. Across visible wavelengths from 400 to 900 nanometers, its spectrum flattens into a neutral gray. As planetary scientist Alan Fitzsimmons has explained with similar objects, this absence tells us 3I Atlas isn't actively outgassing in any strong way. Instead, we are seeing pure reflection bouncing off a surface so dark it has an albedo, or reflectivity, of only 2 to 3%, literally blacker than asphalt. Over millions of years drifting between stars, its surface has been bombarded by cosmic rays, baking carbon molecules into complex, dark organics called tholins. These materials absorb almost every wavelength of light, combining into a neutral gray when seen from a distance. A slight rise in the infrared spectrum suggests the presence of carbon dioxide ice just below the crust, but the signal is incredibly weak. For an interstellar object, that lack of vibrancy isn't emptiness. It's age, a testament to an eons-long journey through the void. This is the color of endurance.
Edge of certainty.
So, how can we be sure this faint smudge is even real? In the raw data, 3I Atlas is barely a whisper above the background noise of space. When you zoom in close enough, honestly, the random static of the sky seems louder than the signal itself. But the difference between noise and a real object comes down to one thing: consistency. Real light behaves with intent. It repeats, it aligns, and it holds a pattern where chaos just cannot. Across multiple long exposures, the faint streak of 3I Atlas appears in the exact same celestial coordinates. Its brightness curve remains stable, even despite atmospheric shifts and thermal noise in the camera. That repeatability is the only reason astronomers can call it real. The data achieved a 5 sigma confidence level, which is the absolute minimum threshold for an official discovery in physics. As astronomer Marco Micheli, who confirmed Oumuamua's strange acceleration, would argue, a persistent signal, no matter how faint, must be treated as a real phenomenon. The final image isn't so much a photograph as it is a mathematical reconstruction, built one photon at a time until, honestly, millions of calculations reduce the chaos into a fragile, undeniable geometry.
Refusing form.
Refusing form. What happens when your discovery refuses to be discovered? Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. Algorithms that measure coma, nucleus and tail just couldn't settle on a pattern. The numbers diverged. In data terms, that means the target is either unstable or the physics behind it doesn't fit our templates. As interstellar object expert Matthew Knight has noted in his research, these visitors often challenge our models. 3I Atlas breaks the logic. Its confirmed hyperbolic orbit, with an eccentricity of roughly 1.1, proves it's not from around here. It behaves like something between 1I Oumuamua, which had no visible coma, and 2I Borisov, which displayed a textbook coma even at 3 astronomical units from the Sun. Its blur is too diffuse to be a solid asteroid but too clean to be an active comet. That ambiguity makes classification nearly impossible using standard cometary models. The picture isn't wrong, it's just showing us a kind of object our instruments and our scientific language weren't built to categorize. It exists in a scientific gray area.
Mathematics of blur.
When an image can't explain itself, You honestly have to trust the numbers. The frame of 3I Atlas is too ambiguous for traditional analysis, so scientists turned to pure mathematics to reveal what the light could not. By plotting its position with micro-arcsecond precision across consecutive nights, they calculated its velocity at roughly 12 kilometers per second relative to the Sun. This confirms a hyperbolic eccentricity of 1.1, the mathematical proof that it's just passing through, moving too fast for our Sun's gravity to ever pull it back. Next, brightness simulations show that if the nucleus is elongated, a slow 11.2-hour tumble could perfectly recreate the uneven brightness we see. Even the blur itself becomes a measurable variable. As orbital dynamicist Davide Farnocchia explains, by deconvolving the image, you can reverse the distortions and find that residual motion smear accounts for about 30% of the elongation, with the rest being the object's actual shape. The image shows uncertainty, but the equations show precisely why it has to look that way.
Distortion or discovery.
Is that a real shape, or just a ghost in the machine? Every astronomical image has them. Cosmic rays can leave small flares, and tiny tracking errors can accumulate and masquerade as structure. When the first image of 3I Atlas was released, that question appeared immediately. How much is the comet, and how much is the instrument? The cylindrical blur could, in part, be a subtle elongation caused by the camera compensating for motion and noise, an effect related to the telescope's point, spread, function. A residual drift of just half a pixel per exposure, when multiplied by dozens of frames, creates a false extension. But not all anomalies vanish under scrutiny. As astronomer Wesley Fraser has explored in his work, consistency is key. When the images were independently processed using different software, the same general elongation remained. The angle of tilt and brightness gradient persisted. That argues against coincidence. If distortion were the only cause, its signature would shift between instruments or processing techniques. Instead, the shape repeated itself, asserting its bizarre geometry through the limits of our observation.
Escaping definition.
At some point, the discussion around 3I/Atlas stopped being about what it looked like and started being about what it refused to be. It is not a traditional comet, it has no coma or tail. It's not an asteroid, its light curve varies too smoothly to come from a simple rocky surface. The image presents something in between, a blur that resists every attempt at interpretation. Its trajectory confirms an interstellar origin, and paradoxically, that certainty of escape is the only thing about it that feels familiar. The data now paints a picture of pure contradiction, a stable brightness curve suggesting a single body, yet an asymmetry that hints at fragments orbiting a shared center. This object is defined by the fact that no existing model can describe it cleanly. As astronomer Matthew Knight puts it, sometimes an object's most important feature is its refusal to conform to our expectations. This forces us to confront the idea that seeing is not the same as knowing, and our categories are only conveniences, not cosmic truths.
Between categories.
So if it defies every category we have, what could it be? This is where scientific observation meets informed imagination. 3I/Atlas sits perfectly between the two prior interstellar visitors. 1I/Oumuamua was sharp and fast. 2I/Borisov was almost too typical. 3I/Atlas is neither, behaving like a memory of both. It's too diffuse to be solid rock, too clean to be a classic comet. It exists in a gap where our definitions fail. It's objects like this that inspire radical new ideas. When data stops fitting patterns, thinkers like Avi Loeb have argued that we must be open to unconventional explanations. While he was referring to Oumuamua, the principle applies here. Is this a new type of dark comet that outgasses materials our instruments can't detect? Could it be a fragment from a tidally disrupted exoplanet, an entirely different class of object? Is it 90% asteroid and 10% comet, or something else entirely? The object is a scientific mystery box. The blur is both evidence and absence, a confirmed detection that withholds its identity, reminding us that our categories are only conveniences, not cosmic truths.
Measured by blur.
When the light from 3I/Atlas finally fades from our sensors, this photograph will be all that remains, a faint smear in an archive. In most sciences, such an image would be dismissed for its lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about this object exists inside that single, unresolved streak. Its speed, its path, its rotation, its distance. From this one imperfect shape, entire models of its journey emerge. We don't know what it looks like, but we know what it's doing. Soon, it will leave our system and recede into the same dark it came from, never to be seen again. This blur is not the beginning of a study, it is the end of accessibility. Paul Chodas of NASA's Kineos has stated that such flybys are fleeting gifts from the galaxy. It's the one clear record of a body from another star crossing through our home, measured by its blur. 3I/Atlas is a visitor that escapes our definitions, a blur that exists in the thin space between what we know and what we can only imagine. What do you think is hiding within that faint smear of light? Share your theories in the comments section below. We're always curious to hear what you think. If you want to continue exploring the universe's greatest unsolved puzzles with us, don't forget to like, subscribe, and hit the bell icon so you won't miss our next deep dive. Thank you for watching Simply Science.